Hello everyone. Today I'll explain geometry camera models. Actually, in second week and third week of this course, I share some moving clips about geometry camera calibration and camera models and image transformation geometrically. So it is it explained before, but I think that geometry camera models is a very important topic in robot and computer vision, and I heard some students that it is not enough to understand. So I think it has better explain these geometry camera models again by myself. So I found some good presentation material to explain more easily. So I hope you can understand some this very important geometry camera models well from this lecture. So overview of today's lecture is as below. Some motivational imaging experiments, and I explain pinhole camera model. It is very fundamental assumption of most camera models, and I'll explain camera metrics, and finally I'll explain geometry camera calibration. So the slides credits, most of the slides were adapted from some Professor Yanis Giorekers from CMU, and some slides inspired from Fredo Durand in MIT. So there are some motivational imaging experiments. Let's say we have a sensor here. It is digital sensor. Maybe it is CCD or CMOS sensor. Then we have a real world object, tree, as shown here. What would an image taken like this look like? This point go to this, but these same points go to everywhere. So as you can see, this same points go to whole of digital sensor. Also, this point also go to the whole digital sensor. So in summary, all scene points contribute to all sensor pixels, as you can see. Okay, so what does the image on the sensor look like? As shown here, you can see we cannot find any specific object, just very bluish, greenish pixels, right? So it is caused by that all scene points contribute to all sensor pixels. So we call it bare sensor imaging. From previous slides, we can notice that we need another device to capture images that reflect real world scene, real world object. So we add this barrier here, and there are some pinhole. Also, it is called as aperture. Maybe we learn what is aperture, right? So what would an image taken like this look like when we have this barrier between real world object and digital sensor? As you can see, most rays are blocked, and very small or one ray goes through this aperture or this pinhole and arrived at digital sensor. as shown here. Okay, let's consider another point here. Also, most other rays are blocked, and some small rays go through this pinhole and arrive at this sensor point. So from this figure, we can know that some is scene points are arrived at some small parts of digital sensor. So ideally speaking, we can say that each scene point contributes to only one sensor pixel. Then what does the image on the sensor look like? It is copy of real world object as shown here, but it is inverted and scaled. It depends on distance from this barrier and the sensor position. Okay, let me explain pinhole camera. Pinhole camera, also known as camera obscura, so in other words, dark room. This pinhole camera first mentioned by Chinese philosopher Moji, and first camera is invented by Greek philosopher Aristotle. You can see this pinhole camera model. Let me explain pinhole camera terms. We have real world object or real world scenes to be captured, and we have digital sensors made by CCD or CMOS sensor, and there is a barrier, and in this barrier we have a pinhole, very small hole, and we call it aperture. And this pinhole is also known as camera center, or we call it center of projection. And this digital sensor is also called as image plane. The distance from this barrier and image plane is called as focal length f, and this focal length is a very important term in camera geometry. What happens as we change the focal length? For example, this focal length is reduced from f to 0.5 f, as shown here. So we can see this ray from this scene point and this scene point before the image is located here, because image plane was here, but image plane moved to this, so closer to this barrier. Then you can see object projection is half the size as shown here. So by changing this focal length, we can enlarge the scene, or we can make the scene small as shown here by changing this focal length. So what is an optimal pinhole size? Ideally, as I said, this scene point from here should become to single pixel point in this image plane. For that purpose, pinner has infinitesimally very small size. But in practice, it is impossible. We cannot make it. So there are physically some possible size. So what happened as we change the pinhole diameter, as shown here? Then, okay, in the small pinhole size, we have these images, but there are other rays go through this more some larger pinhole. Then image become blurred. Maybe I explained this in camera imaging pipeline. So this means we use larger aperture, then we have this blurry result. Let's look at light efficiency. For this configuration, real world and specific pinhole diameter and specific focal length f, what is the effect of doubling the pinhole diameter like this? And what is the effect of doubling the focal length? So focal length is more far from here. So it is 4 times more light when we have 2 times pinhole diameter, and 1/4 times less light when we increase 2 times focal length, because the ray goes more far from this pinhole, so the amount of light become reduced. So practically we use lens instead of pinhole. Yeah, pinhole is some ideally we assume that there are very infinitesimal pinhole, and most of camera model will be explained based on pinhole camera model because it is very simple and effective to be explained. But practically, we cannot make very small infinitesimal pinhole size. So instead of those pinholes, we use this lens. So this lens map bundle of rays from point of scene to the sensor. So when we make this lens well, then this lens can make some good approximation to pinhole camera model. So how does this mapping work exactly? Let's see this pinhole camera model again. There are some rays from this scene point and this scene point, and pinhole camera has very small slit as shown here. Only this scene point is goes through this, and only this ray goes through this. So we can obtain this reversed and well focused image. Let's see the lens. So the constraint of this lens camera is that they want to make the same image as the pinhole camera model. So starting from this scene point, there are the ray is we cannot control this ray because it is the characteristics of ray light. So from this scene point, there are a bunch of these rays as shown here. But this lens, okay, so all of rays from this scene point to lens should be focused on this point as shown here. And for another scene point, as you can see, from here there are also bunch of rays and it goes through this range. And also our goal is that the goal of the lens, it should be focused on this point. All of rays from this same point should be go to this point in the image plane. So when we can make this lens to focus something like that, as you show in this figure, then yeah, physically it is a different system, but we can approximate this user and practical lens system to pinhole camera model. When you see the pinhole camera model again, the central rays propagate in the same way for both models, right? So the difference is pinhole cameras make a barrier for other rays, but the lens camera system, they make good lens, so these other rays from the same point also focused on this point. Therefore, let's describe both lens and pinhole camera model in this single slide. So we can derive properties and descriptions that hold for both camera models if we use only central rays. So yeah, in real situation for this range, they receive many rays, but when you assume that the lens camera is in focus, so yeah, it is also some ideal case, but when you assume that this lens can to be focused of all of from the same point, and there is all these rays, and when this lens go all of these rays into focused into this image point, then it is the same as we only use these central rays. So yeah, all of these cases are also two lens case and pinhole camera case. They are also ideal case. But when you think which one is more practical, then this is more practical instead of this pinhole camera model. So in equation and derivation for camera models and epipolar geometry stereo case, we assume that we use this pinhole camera model. So we use derivation from the pinhole camera model, but I think it is good to you to know that real camera system use this kind of lens, but the lens can make the image similar to pinhole camera model. That's what I'm saying in this explanation. Let's see the important difference between pinhole camera model and lens camera model. It is the focal length. In a pinhole camera, focal length is distance between this aperture, barrier, and image sensor, image plane. So it is f from here to here. But for a lens camera, focal length is not this image plane, but to here. This point is where parallel rays intersect. So focal length is reduced half of this focal distance, d prime. So it is the important difference. So you remember it. Let me summarize this lens and pinhole cameras model. We can derive properties and description that hold for both camera model if we only use central rays for both model, and it is done by assuming the lens camera is in focus, as shown here. So in this case, we assume ideal lens model, but usually the lens can be made well. So this assumption, in some sense, is valid. So we can use this pinhole camera model and lens camera model without some difference in mathematical derivation. Also, we assume that the focal distance of the lens camera is equal to the focal length of the pinhole camera as explained in previous slide. So the focal length of lens camera is half of focal length of the pinhole camera. But you remember, focal length f refers to different things for lens and pinhole camera, right? It is half. But in this lecture, as I said, we will use the derivation in pinhole camera model because it is more direct and easy to explain. So we use this focal length to the aperture sensor difference as in the pinhole camera case, even though we use lens camera. Now I can explain a camera matrix. It is very important to understand the relationship between 3D points and 2D points. For example, for robot vision, a robot equipped with a camera moves from some spot to another spot. Then our goal for robot vision or computer vision is that we want to know the whole camera trajectory from starting point to end point. Also, we want to know 3D scene structure in that environment. It is very important for robot. The robot should know where I am and also which object or which environment is. So for understanding those geometric information around the robot, the camera matrix is our starting point to derive further estimating motion and 3D construction. We can regard the camera as a coordinate transformation. A camera is a mapping from the 3D world to a 2D image. In this figure, this 3D object or 3D scene is transformed to this 2D image. So this camera performs a role of 3D to 3D 2D transform. And when we transform from this 2D image to another 2D image, we call it image warping. So we already learned this image warping in the previous lecture. From the simple pinhole camera model, finally we get this simple equation. This P is camera matrix and this capital X is 3D world point and this small x is a 2D image point, and this small x and large x, we call it homogeneous coordinate. So let's look what are the dimensions of each variable. We learned homogeneous coordinate in the previous lecture. So this image coordinate, usually we have two values, x or y, but in homogeneous coordinate, we can write down this xyz for image coordinate. So the dimension is 3 by 1. And homogeneous world coordinate also usually three values, x and y and z, but in homogeneous coordinate, it has 4 values. So it is 4 by 1 dimension. Then this camera matrix is explains the mapping from this 4 by 1 matrix to 3 by 1. So it has, as you can see, 3 by 4 dimension for camera matrix P. It is very important. Let me revisit the pinhole camera model as shown in this figure to explain previous equation. Small x is equal to camera mass P multiplied by large X. This is real world object, and each ray is through this optical center or pinhole, and this image plane is apart from the focal length f. Okay, we let this f equal to 1, focal length is 1. Then this figure shows rearranged pinhole camera model. So same distance, it is not reversed. So virtually, yeah, physically the image is mapped to here, but virtually we can think image plane is here, just scaled version of this real object to this virtual image plane, and the distance from this barrier is focal length f, and it is assumed 1. Now we can redraw the previous figure into this coordinate axis. So this small low letter x, y, g correspond to image plane. So this is camera center, and this is principal axis, and this is image plane. And this upper letter x, it corresponds to world coordinate. So this camera matrix is transformed from world coordinate, 3D point in the world coordinate, into image plane in the image plane or camera plane. So this image plane is at the z equal to 1 because we let focal length f is equal to 1. So what is the equation for image coordinate x in terms of 3D point x? Let's see 2D projected view from the previous figure. This is 3D camera point upper letter x, and this is image plane. So this value is y and this value is g. So we want to know the coordinate of this point. It is from this 3D point is projected to the central projection, and this is the projection point of this upper letter x into this image plane. So what is the equation for image coordinate x in terms of this capital letter x? It is this. It's very simple proportional expression because this is y and this is g, then this is 1, so this is just y over g, and also for x is the same because we can draw the same 2D view. So this 3D point x, y, z is mapped to this x over g and y over g in image plane. So we can think this equation is the equation of projection of this 3D point x into this image plane. In the previous slide, we derived the relationship between the 3D point x and 2D point low letter x in this image plane. So what is the camera matrix P for pinhole camera model to satisfy this equation x equal to px? From the derivation, we know that this 3D point is mapped to this 2D point, and by applying homogeneous coordinate, this xyz 3D point become this 4x1 matrix xyz1, and we can rewrite this x over g and y over g into the homogeneous coordinate as shown here, x, y, g. So general camera model, we can write the relationship between 3D point and 2D point, projected point, and the dimension is 4x1 and 3x1. So camera position matrix or camera matrix can be written as this 3x4 matrix. The number of elements is 12. What does the very simple pinhole camera projection look like? So how can we know the value of this P matrix is here, as shown here. So from this relationship, we can determine the value of each element of camera matrix P. So P1 is equal to 1 and P6 equal to 1 and P11 equal to 1 and other values are 0. So when you apply this matrix and this, then this equation is the same as this projection relationship. And we can rewrite, because this is 3x3 identity matrix, so we can rewrite this P matrix into this I and 0. It is an alternative way to write the same thing. Let's consider more general case. Previously, we assumed that focal length f equal to 0. Then how it will be when this focal length is just arbitrary value f? So what is the equation for image coordinate x in terms of this capital X? Previously it is x over g and y over g, and it is changed from 1 to f. So the value of this mapping point in the image plane is f multiplied by x over g and f multiplied by y over g. So the relationship from triangles is changed into, as shown here. So 3D point in the world coordinate is projected to this 2D point in the image coordinate. Value is f multiplied by x over g and f multiplied by y over g. Then in this camera matrix equation, this p, the value of p is changed as shown here. So 1 is changed into f. Also, this value become f, and this is the same, 1. So the pinhole camera projection matrix is changed into this value. We can generalize the camera matrix further. In general, actually previously we assumed that the coordinate of image plane and coordinate of camera plane are the same, but it can be different, right? So the camera and image have different coordinate system as shown here. So actually we have 3 coordinate systems. First, world coordinates, and there are 3D points, 3D world points, and there is camera coordinate. So this world point is projected to this camera center, but there are another points because it is image plane coordinates. So image is mapped to the image plane coordinates. So you can see the camera origin and image origin may be different. For our goal is just to use the image. So our derivation should be summarized in the image coordinate system, but the projection center is defined in camera coordinate system. So we moved that origin from camera coordinate system into image coordinate system. So when we define that distance from camera coordinate system to image coordinate system as this p, then how does the camera matrix changes from this as shown here? So this px and py is the shift vector transforming camera origin to image origin. We can decompose the camera matrix like this. This is consists of focal length and this distance from camera origin to image origin, and we have another this identity and zero matrix. So this is very usual form when we explain camera matrix. So both of matrix is homogeneous, and this left matrix is transformation from 2D to 2D and accounting for some arbitrary focal length and origin shift. And this, so we call it, this matrix is intrinsic matrix. It is related with the inside value of camera. And this is perspective projection from 3D to 3D, assuming image plane at g equal to 0, and shared camera and image origin. So we call this matrix is extrinsic matrix. So it is kind of relationship between image world coordinate and camera coordinate. This matrix also written as here, so k and I0, where k equal to this. So we refer k as intrinsic matrix, and this I0 is extrinsic parameter, extrinsic matrix. As I said before, in general, there are three generally different coordinate systems. We have world coordinate, and this world point x is represented in this world coordinate, and there is a camera coordinate, and there is an image coordinate. So we have three different coordinates. We need to know the transformations between them. Let me explain world to camera coordinate system transformation. This is world coordinate system. So we have this W, and this XW tilde means heterogeneous or inhomogeneous coordinate. So the value is 3 values, not 4. This is camera coordinate system. So this is C is here, and this is image plane, right? Then the coordinate of the camera center in the world coordinate frame. So the vector from this world coordinate system into camera coordinate system can be written as tilde C, right? This point is 3D point in camera coordinate system, and this point in world coordinate system is translated to, as shown here, this equation. So this tilde W XW minus tilde C is the translation from world coordinate to camera coordinate. So why these 2 points are not aligned? It is because of rotation. These 2 coordinate systems may have rotation difference. So by multiplying this rotation value, rotation matrix, 3 by 3 matrix, now points are coincided. Now we can explain the relationship between 3D point in world coordinate and 3D point in camera coordinate using rotation matrix and the vector from translation from world coordinate to camera coordinate. But this tilde is inhomogeneous coordinate, heterogeneous coordinate. Then how do we write this transformation in homogeneous coordinates? We have this equation. We can write this 3 by 1 matrix into 4 by 1 matrix, and this R and this tilde C can be written as this. There are some typo, it is tilde C, so we can write this in homogeneous coordinate. So homogeneous coordinate of 3D point in camera coordinate is multiplied by this 4 by 4 matrix and this homogeneous coordinate in world coordinate. The previous camera matrix is for homogeneous 3D coordinate in camera coordinate system. as shown here. Image, the point in the 2D point in image plane is camera matrix P multiplied by the 3D point in camera coordinate, and this P matrix can be written as this intrinsic parameter and extrinsic parameter. Also, in the previous slides, we can show that this 3D point in camera coordinate can be written as this. The world coordinate point is transformed to the camera coordinate point by multiplying this 4x4 matrix. It consists of rotation and translation between camera and world coordinates, right? Now, let's wrap up. We can write everything into a single projection. Finally, this 2D point in image plane can be represented by camera matrix and 3D point in world coordinate. So it consists of this matrix. We call it intrinsic parameter 3x3 matrix. It corresponds to camera internals, and it is image to image transformation. So it consists focal length and some difference between camera and image coordinate. And this matrix is perspective projection 3x4 matrix. It maps 3D to 2D points. So it is camera to image transformation. And this is extrinsic parameters, and it corresponds to camera externals. So it explains world to camera transformation. So this equation is very important to understand the camera geometries. We can rewrite the previous equation as shown here. So this is intrinsic parameters corresponds to camera internals, focal length, and the difference between camera and image coordinate, origin. And this is extrinsic parameter corresponds to camera externals, world to image transformation. We can decompose the camera matrix like this. So this is translate first and then rotate. Or we have another way to write the mapping. So when we let this t equal to minus rc, then rotate first and then translate. Usually this is more popular to me. So, but it's okay. Both of things can be used. But usually this P matrix is expressed by KRT. So intrinsic parameter and rotation and translation. General pinhole camera matrix can be written as P equal to KRT, and intrinsic parameter consists of focal length and the transformation of origin, and extrinsic parameter consists of 3D rotation, 3x3 matrix of R, and 3x1 matrix T, 3D translation. The following is the standard camera matrix we saw. However, CCD camera, in CCD camera or CMOS camera, pixel may not be square. So in that case, we cannot use single value of f, but we have focal length for each axis, x and y. So alpha x is focal length in x-axis, and alpha y is the focal length in y-axis. How many degrees of freedom? It is 10. There are 4 degrees of freedom for intrinsic matrix, and 3 for rotation, and 3 for translation. So 4, 3, 3. Now we have 10 degrees of freedom, right? There is another generalization of camera matrix. From the previous slides, we assume that sensor is squared, but sensor may be skewed. Like sensor becomes like parallelogram. Then we have another parameter, this S, skew parameter. Then how many degrees of freedom? 11, right? So usually this camera matrix has 11 degrees of freedom. Now we understand camera matrix. So let's go to geometry camera calibration. Maybe if you use some camera, then you can hear somewhere camera calibration, geometry camera calibration. So it is very simple. The geometry camera calibration is to estimate camera matrix P. Yeah, it's simple, right? From some data set, from some capture, some patterns, and there are some assumption of 3D points, and we have 2D images, and we know the relationship between 3D and 2D points. Then finally, we have the camera matrix, the relationship between 3D points and 2D mapping points. This table shows the difference between camera calibration, triangulation, and reconstruction. And this camera calibration, also known as pose estimation. For this camera calibration, we assume that structure or scene geometry is already known. So by measuring the 3D to 2D correspondences, we estimate motion, or we estimate camera geometry, P matrix, camera matrix. And triangulation is some contrary to camera calibration. So in triangulation, we have 2D to 2D correspondences, and also we know the camera matrix. It means that already camera calibrated. Then the goal of triangulation is estimate scene structure, scene geometry. And the 3D reconstruction, we call 3D reconstruction. It is also based on 2D to 2D correspondences, but there is no known thing of motion and structure. So we estimate structure as well as motion. So in other words, this 3D reconstruction is structure from motion. Maybe you hear this word. So it means that from 2D to 2D correspondences, we estimate motion, and from motion, we estimate structure, and also from structure, we can have more accurate motion. So these two parts are very complementary. So this search for motion is very interesting technology, very interesting algorithms, but it is very hard to estimate accurately. Let's see the example of pose estimation. For given a single image, we estimate the exact position of the photographer. So for these buildings, when we go to some trip, we take many pictures in this scene. As you can see, there are so many images here, and the goal of pose estimation is, as you can see, to estimate the exact position of camera or photographer. You can see. Also, we call it camera calibration for this process. Let me explain geometry camera calibration. Given a set of matched points in 3D space and in image plane, we use this camera model. So the projection model is X and P, and we can written by column P multiplied by 3D point X. So the goal of geometric camera calibration is to find the estimate of this P camera matrix. So we'll use a perspective camera model for pose estimation. In previous lecture, maybe first or second or third lecture, we learned homography. It is plane to plane transformation. So it is represented by 3 by 3 homography matrix. So using this 3 by 3 homography matrix, we can transform from a plane to another plane. So it is very similar setup as homography estimation, but as you know, the degrees of freedom is different. For homography, we have 8 degrees of freedom, but the camera matrix, we have 11 degrees of freedom. So slightly different derivation for camera matrix estimation. We have this equation, some image coordinate and 3D coordinate. We unknown is 3 by 4 camera matrix. So unknown is 12, but the degree of freedom is 11. So we can rewrite this row is P1 transport and P2 transport and P3 transport. Then by using heterogeneous coordinate, this x prime is represented by this P1 transpose X by P3 transpose X, and Y prime is similarly represented by this. So this is non-linear relationship between coordinate. So how can we make these relations linear? Because linear equation can be solved more easily and more directly. So for most cases, we prefer linear equation instead of non-linear equation. So this is non-linear equation, as you can see, but make them linear with algebraic manipulation. So we multiply this to this and this to this. Then we have this these two equations, and as you can see, these two equations are linear. Now we can set up a system of linear equations with multiple point correspondences. Because the degree of freedom is 11, so we need more point correspondences to estimate this P matrix. Okay, now we have these two linear equations. So how do we proceed? We can rewrite this linear equation into our matrix form, as you can see. So there are, it is same as camera matrix, P1 and P2 and P3, but it is vertically concatenated. So this is like P11, P12, P13, P14, P21, P22, P3. So as you can see, it is 12 by 1 matrix. And this is 3D points, and this is 3D points multiplied by 2 points. So also this row is 1 by 12 row matrix. So for this, we have 2 degrees of freedom, right? So how do we proceed from this equation? When you have n points, then we can stack all of points as shown here. For single point, we can have this equation, and so we have n points, then we have 2 multiplied by n rows, right? So when you have more than 5 points, 5 correspondences between 3D and 2D points, then we can estimate this element of P matrix. So how do we solve this system usually? We use SVD, singular value decomposition. Maybe you can learn this in linear algebra. So this is the equation, some solving equation. So we substitute to the L2 norm of x equal to 1, because the degree of freedom of this is 11, but the element of this is 12, so we have one scale factor. So for this scale factor, we need some kind of normalization. So the norm of L2 norm of this x equal to 1 is kind of, we can determine the scale factor. And we want minimize this ax, because our equation is ax equal to 0. So by minimizing this value of ax, finding this ax, then it is some algebraically minimal solution for this equation. So finally we can have P matrix by solving this equation using SVD. After applying SVD to A matrix, we can decompose as shown here, and this sigma indicates singular values. So the solution of x is the column vector of V corresponding to smallest singular value, right? Equivalently, solution x is the eigenvector corresponding to smallest eigenvalue of this A transpose A. So we can use SVD or eigenvalue decomposition, but usually this estimation of eigenvector and eigenvalue is more computational cost. So usually we use SVD to solve this AX equal to 0 equation. Okay, so we assume that we have more than 5 3D and 2D points correspondences. It is known. Then we can have A matrix, and by using SVD or eigenvalue decomposition, now we have this P matrix, right? We can have these 12 elements and degree of freedom is 11. So now we are done? Not yet, because how do we get the intrinsic and extrinsic parameters from this camera matrix, projection matrix? We want to know like some relationship between world coordinate and camera coordinate. Also, we want to know the focal length and central projection in some applications. We simply divide this projection matrix into 3 by 3 and 3 by 1. We write this P matrix as KRT, intrinsic and rotation and translation. Then we can rewrite this R and minus RC. C is camera center, central projection. And this K is multiplied by this and this. So M is KR, and then we can rewrite this P matrix as shown here. So we want to find the camera center C. What is the projection of the camera center? Actually, P is the all points is come to C, kind of mapping function, some points in 3D, and the origin is C. So C is the origin of this projection. So this PC should be equal to 0. Then how do we compute the camera center from this PC equal to 0? We can use SVD. So similarly, this C is eigenvector corresponding to smallest eigenvalue. Now we can have C, camera center. Then we want to find intrinsic matrix K and rotation R. So as I said, M is equal to KR. So M is the multiplication of intrinsic parameters and rotation matrix. So any useful properties of K and R we can use. Maybe you know K is right upper triangle. So there are 3 by 3 matrix of K, but only right upper triangular value has some value, and another value is 0, right? So this 6 value is non-zero, but these 3 values are 0. So we call it right upper triangular matrix. So K satisfies this constraint, right upper triangle. And also this R, rotation matrix R, should be orthogonal. It is the important property of rotation matrix. So based on these two constraints, how do we find K and R? We can use QR decomposition. Okay. Now we understand from the matches between 3D and 2D points, we can estimate P matrix, and from P matrix we can know intrinsic parameter K and the center of projection C and rotation matrix R. So we know whole of camera geometries. Then where do we get these matched points from? These correspondences between points in 3D and points in the image. For calibration, we need a reference object, as shown here. So we call it camera calibration pattern or camera calibration object. So we place a known object in the scene and capture this scene by camera, and we should identify the points in here to points of images. So we should know the accurate 3D coordinate of this point, this point, and also we should know this point is corresponding to the point in the image. So we compute mapping from scene to image. So there are some issues. We should know geometry very accurately. So the position, real position of this point should be very accurate, like less than millimeter accuracy, like micrometer. Okay. Also, we should know 3D to 2D correspondence. So maybe it can be done automatically, or some human can annotate the correspondences between 3D points and 2D images, like clicking these images. Clicking these images, we can add the coordinate, real 3D coordinate over here. Also, click this point, and we can know the real 3D points of this. So we repeat it for whole points. Then we can apply our previous derivation of estimating camera matrix, projection matrix P, right? Let me summarize geometry camera calibration. The advantages of camera calibration are very simple to formulate because it is linear, so we can use SVD, and we have analytic solution. But there are some disadvantages. They don't have, they they did not consider radial distortion. Also, harder to impose constraints. Yeah, it is the disadvantage of most of the linear solution. We cannot impose. It is harder to impose constraints to linear equation. Also, it does not minimize the correct error function. It is just minimize algebraic error. So minimizing algebraic error does not mean the minimizing geometric errors. We want to minimize geometrically, not that algebraically. So it is somewhat discrepancy between the errors. For these regions, non-linear methods also used. It is somewhat, they are prepared. So we can define error function E between projected 3D point and real image position. Then this E is become non-linear function of intrinsics and extrinsics, and also radial distortion. So we can minimize error function E using non-linear optimization technique like Levenberger-Marquardt or Gaussian-Newton, semi-deposit programming, etc. So this shows the minimizing reflection error. This 3D point P, by using the estimated P, we can have projected point here. And also another P1, we have projected point here. So we want to minimize real image point and this projected point. So, so this distance we call geometric error. So it is more meaningful than the algebraic error. So it is somewhat different. The minimizing direction is different from algebraically. But for most cases, this error is more some better for using geometrical applications like structure promotion or SLAM. So the error value, like the mean of this distance, is widely used to express the accuracy of camera calibration, like less than 1 pixel error of these projections. Then it's very accurate, right? Okay, finally, let me explain what is the radial distortion. So, what caused this distortion when you capture these images? As you can see, this line is usually like become curved. Yeah, in real scene, it is straight line, but when you capture the images, this line become curved, as you can see. This also. So this is no distortion. Line is line. Straight line becomes line. But this is better distortion, and this is pincushion distortion. Usually radial distortion is similar to this better distortion, right? You can see the similar between these images and this better distortion. So let's see the radial distortion model. Ideally, x prime is like f multiplied by x over g, and y prime is f multiplied by y over g. But it is distorted. The amount of distortion is 1 over lambda, and this lambda is the equation of this r. So this r is distance from the center of these images and this point. This is r. So it means that when we have close to the center of image plane, then the distortion is small. And when we have some more distance from the center, image center, then as you can see, this value of r is large, become large, and lambda become large, so the distortion becomes severe. So this radial distortion depends on the distance from the center of image. So we can minimize the reflection error with radial distortion. So in the previously, we only minimize between image point and reprojected point by estimated camera matrix P. Then we multiplied by this 1 over lambda radial distortion parameter. So by minimizing this equation, then we can have another parameter lambda, the amount of radial distortion. So by minimizing this equation, we can have P as well as lambda. So now we can remove the radial distortion by minimizing this equation. So by applying the inverse of lambda, actually we apply 1 over lambda, then by applying lambda, we can have this reduced radial distortion images. So input images is as shown here, so you can see very severe curved scene, but by applying the minimizing the radial distortion, you can have this line, straight line becomes straight line. So actually this radial distortion is severe to some when you use short focal length. So but when you use some large focal length, so it means that we can see some very distant scene, then the effect of the radial distortion is not severe. So we should consider the radial distortion when we capture very near object or near scene, as shown here. And otherwise, in some sense, it is not that case. But usually, when you use camera for some slam or search promotion, like some motion trajectory estimation, we usually see near scene points. So it means that we should consider the radial distortion for that scene, right? We already see the calibration using like some 3D plane, right? We have like this plane and some points, and we assume that we know the accurate 3D coordinate of this all of these points. So it is one approach to calibrate the camera, but most popular is using plane. So maybe you see this color checker pattern. So by capturing like more than 10, then we can also have the camera calibration matrix, camera matrix. So the advantages of this multi-plane calibration are only requires a plane, and we don't have to know position or orientations. And there are so many good code available. So there are very famous MATLAB code. Also, this code is included in OpenCV, so you can use this code using by OpenCV. But the disadvantage is it needs to solve nonlinear optimization problem. But you know we have already code, so you don't consider this nonlinear optimization. It already implemented some by the good persons, so we just use it, yeah, without implementation. So let's just see the step-by-step demonstration to this multi-plane based calibration. So we capture, in this case, we capture 20 images. And as you can see, it is very important. You should change the orientation of patterns. As you can see, some this, and you rotate the patterns, and you tilt the patterns. Also, you leftly slighted and lightly rotated. So you should change these kind of things because each point here is the 3D point. So by changing the pose of this pattern, we can have more robust estimation of camera matrix. So when you capture this calibration checker pattern, you should change the pose as shown here. And then we should know that from the input image, we should know the real 3D point, right? For that purpose, for these input images, we click to this and another click and also third click and fourth click. Then we know this is the pattern. Then automatically they detect the corner points of all these patterns, as you can see. So this you can see this red cross of all patterns, right? Then we already know the 3D coordinate of this point. So by detecting this corner point, we can estimate camera metrics automatically. So by estimating pressure metrics, we can reproject the 3D points into 2D images. So this red cross is real image point, real image corner point, and this yellow circle indicates reprojected grid point. So as you can see, it is very similar, very near. So when there are somewhat error in this point, but usually all points coincide, right? This red cross and these yellow circles, they are coincided. It means that the calibration process estimating camera metrics are accurately done, right? Uh, Previous slide, we captured 20 images. So this shows the pose of each patterns. Because estimating the camera metrics, we should know the pose of these patterns. So it is 1 to 20, we can estimate the pose of these patterns in this camera coordinate, right? And this shows some exchange parameters. So for this image plane, we can know the rotation and the position of center, right? So by some calibration, we know all of these exchange parameters for each images. But it is not used. It is just showing that the process of camera calibration are well done by showing this position and orientation. Okay, let me summarize what does it mean to calibrate a camera calibration. There are many different ways to calibrate a camera. So this lecture, we run this geometry calibration. I think it is most important calibration step, geometrically calibration. And we learned this radiometric calibration and color calibration and noise calibration partially in camera imaging pipeline lecture. Maybe when you want to know more details, then let me know. When you send some email, then I will let you know the good references to understand this radiometric calibration and color calibration and noise calibration. Also, today we learn some radial distortion. It is one of range calibration steps, but there are another some calibration steps to range. So also if you have want to know more details, then let me know. I will also let you know another related references to range calibration. So today I finished today's lecture. We understand the pinhole camera model and camera metrics. Finally, we learn how to calibrate a camera. It is estimating camera metrics, right? So next lecture, we will learn epipolar geometry. So it assumes that we have two cameras, like stereo cameras. Then how do we derive the geometric relationship between these two images? We call it epipolar geometry. So we will learn this epipolar geometry next lecture. So thank you for listening. Bye.